In chapter 19, problem 1 says to describe the elements of Q adjoin the cube root of 5. So you'd want to think of Q, the rationals, as being a subfield of either the reals or the complex numbers. It really doesn't matter, in this case at least. And pretend you know what the cube root of 5 is. There's no issues with real analysis, like trying to guarantee the cube root of 5 exists. You know it exists. You're going to assume it exists. There is a number, a real number, whose cube is 5, in fact, a positive real number. And you're going to adjoin it. That does not mean take all the rationals and add one element to it. It's many more elements besides just cube root of 5. That was my first mistake when I was thinking about and learning these things, was I thought you just added that one element. I was confused. Okay, instead, this is, by definition, the smallest subfield of, you could describe it again, either as the real numbers or the complex numbers. In general, I think it'll be safer to use the complex numbers, so to speak. For example, if we want to adjoin the imaginary unit I. So the smallest subfield of C containing the rationals and cube root of 5. Maybe that description made me think, okay, yeah, you just got to stick cube root of 5 in there. But that's incorrect. If cube root of, here's one example that illustrates why it's incorrect. I will write cube root of 5 also aside to the 1/3. It's because it's a field, by definition, it's the smallest subfield of the rationals containing, of the complex numbers containing all the rationals in this. Because it is a field, it's closed under addition and multiplication. And so if it contains cube root of 5, it also contains its square, for one thing, because of closure under multiplication. Also contains cube root of 5 squared. I'll write that as 5 to the 1/3 squared, which is 5 to the 2/3. And 5 to the 1/3 cubed, which is 5, which we already include in the rationals, so I don't need to write that. But it would also include 5 to the 1/3 to the 4th power, 5 to the 4/3, etc. It would also contain 5 to the 1/3 plus itself, which is 2 times 5 to the 1/3, etc. It contains infinitely many new elements, you might say, not just one new element. How do you describe this field beyond what I just said? There's a theorem. It's related to an irreducible polynomial that this thing is a root of. Cube root of 5, 5 to the 1/3, is a root of 0 of, for example, f of x equals x cubed minus 5. And that cubic polynomial is irreducible over Q. Why? Eisenstein's criterion. This is irreducible over the rationals by Eisenstein, not Einstein, but Eisenstein's criterion. What did Eisenstein's criterion say? If you've got a polynomial with integer coefficients like this does, 1 is the coefficient of x cubed, -5 is a constant term, all the other coefficients are technically zeros. And if you can find a prime p that does not divide the leading coefficient, but it does divide all the other coefficients. So it does not divide 1, but it does divide 0, and it also divides -5. Oh, 5 pops into mind as your prime. And also so that p squared, in this case 5 squared, does not divide the constant term. It's kind of a funny condition. Then Eisenstein's criterion says this is going to be irreducible over the rationals. Strange criterion, but true. This fact does mean a certain theorem in chapter 19 applies. this theorem is what I'm thinking of in particular. Let's take a look at this theorem. Let F be a field like the rationals. Let's go ahead and, as you read this, pretend F is the rationals. Let P of X in F of X, meaning coefficients from the field. Our coefficients are integers, so they are also rational numbers. Be irreducible over F, be irreducible over the rationals like our example is. If A is a zero of P of X in some extension E of F, oh, this is going to be the E here. Cube root of 5 is a zero of that thing, and it will be in this field. Then, yeah, if you adjoin that root, you can say it's isomorphic to a certain factor ring, which is a field. Furthermore, here's the part I want to focus on. If the degree of the polynomial that is irreducible is n, our polynomial's degree 3, then every member of this field extension can be uniquely expressed in this form as a linear combination of the powers of A. How many powers? Up through the n minus 1 power. Our polynomial here has degree n equals 3. Therefore, we go through the n minus 1, 3 minus 1, or second power. Q adjoin Q root of 5 could be thought of as the set of all linear combinations. All right, C sub 2, the A from the theorem is the Q root of 5, 5 to the 1/3. If I raise 5 to the 1/3 to the second power, I get 5 to the 2/3. All linear combinations of these powers of the A is 5 to the 1/3 power. You also include 1 as one of the powers that you're talking about, C0 times 1. And the C's are from this base field, from the starting field, which is the rationals in this case. These C's, C0, C1, C2, are rational numbers. That's what the problem is after. That's our description of this field, this smallest subfield of the complex numbers containing all the rationals and the cube root of 5. This is an algebraic description of it. This is also enough to say that this set of 3 elements, 5 to the 2/3, 5 to the 1/3, and 1, I'm writing them in that order, but it is a set, so I could write them in the other order. 1, 5 to the 1/3, 5 to the 2/3, is a basis for this field as a vector space over the rationals. Why? Well, first of all, the fact that this rationals adjoin the cube root of 5 equals this set is enough to say this collection of numbers, which are vectors in this vector space, spans, because what is a span? It's the set of all linear combinations. Where these scalars are rational numbers in this case, that's a vector space over the rationals. It's any field will be a vector space over any subfield of it. Okay, that was an important example back in the old chapter 19 from the previous edition. Is it also going to be linearly independent? It will be. That's not actually stated in this theorem, but the fact that you get unique representation, that this representation is a linear combination is unique, is equivalent to being a linearly independent set, these powers of A being linearly independent. The only way this kind of linear combination is going to equal the number 0 is if all the coefficients are 0, when I assume those coefficients are rational numbers. This also means the dimension of Q adjoin the cube root of 5 as a vector space over Q is 3, because it's got a basis with 3 elements. In chapter 20, this is called the degree of the extension. degree of extension. And there's another notation for this that's reminiscent of notation for the index of a subgroup in a group. You write it like this, except we use square brackets instead of just vertical lines. This notation is the notation for this degree. I'll point out where it is in chapter 20. This definition is from chapter 20, the degree of an extension. Let E be an extension field of F. So F is the base field, the smaller field, so to speak. E is the bigger field. We say E has degree n over F and write this notation, reminiscent, again, of the index notation with subgroups and groups, but not the exact same thing. We write that equals n if E has dimension n as a vector space over F. Furthermore, if that number happens to be finite, like for example, it's 3, then it's called a finite extension. Doesn't mean there's finitely many elements added to it, right? I've already emphasized that. But you still call it a finite extension, even though we're dealing with the infinite sets. Otherwise, if that degree is not finite, we call it an infinite extension. We mostly deal with finite extensions. Those are definitely simpler. Okay, so this is the answer to problem 1. That's your description. But I wanted to add some stuff to it to relate it to vector spaces and also content from chapter 20 about degree of extensions. I can also relate it to more content from chapter 20. This is also something called an algebraic extension. Q adjoining Q root of 5 is an algebraic extension of the rationals. What does that mean? It means every element of this extension field satisfies, is a 0 or root of some polynomial with coefficients from Q. The algebraic extension of Q, i.e., every element of Q adjoin Q root of 5 is algebraic over Q, which, what does that mean? Meaning every element, it's kind of wordy, but I think it's worthwhile, of this extension field is a root or 0 of some polynomial f of x with coefficients that are rational. That's what it means to be algebraic. We can contrast this with non-algebraic extensions, which are called transcendental extensions. Here's a contrast. Q adjoin pi. The number pi, which you've known about since whatever, 4th, 5th, 6th grade, is not an algebraic extension of Q. It is still same notation as before. It is still the smallest subfield of, say, the complex numbers or the real numbers, since pi is real, containing all the rationals and also containing pi. But it turns out pi is not an algebraic number. It does not satisfy any polynomial equation with coefficients from Q. That takes proof. The proof is super duper hard. People suspected this for a long time, through the 14, 15, 16, 1700s. Took until the late 1800s for somebody to actually prove it, that pi did not satisfy any polynomial equation with coefficients from Q. This is not algebraic, not an algebraic extension of Q. Not. In particular, pi is not algebraic. Pi is transcendental, we say. Transcendental is the word for not algebraic over Q. And that means it does not satisfy any polynomial equation with coefficients from Q. It satisfies polynomial equations with real coefficients. For example, it satisfies, it's a 0 of x minus pi, but that's cheating, right? Pi is not a rational number. Pi is irrational. Square root of 2 is irrational as well. Cube root of 5 is irrational. What's the difference? Well, they're both, cube root of 5 and pi are both irrational. They're not rational numbers, but still somehow as irrational numbers, they're different. Algebraic versus non-algebraic. You could kind of picture it this way. Imagine this box representing the real numbers, and you've got a sub box of it, a subset of it representing the rational numbers. Everything over here in this shape is irrational. That set is the reals, take away the rationals. That's the irrational numbers. There are some irrational numbers that are algebraic and some that are not. All rational numbers are algebraic. This set represents the algebraic numbers. Every rational number is algebraic, but there are some irrationals that are algebraic, like square root of 2 or cube root of 5. But there are plenty that are not algebraic, like pi or e, things like that, or numbers you've just never even thought of before. You will learn in real analysis, actually, that this picture is somewhat indicative of the fact that even though both the rationals and the reals and the algebraic and the transcendentals are all infinite sets, in some precise sense that you'll learn about in real analysis, the rationals are a smaller size of infinity than the reals, and therefore also the irrationals. And in fact, the algebraic numbers are a smaller size of infinity than compared to the transcendental numbers. It's hard to prove any particular number is transcendental. Took a lot of work to prove pi is transcendental. E is transcendental. That took a lot of work. The author mentions nobody to this day knows whether pi plus e is transcendental. It's hard work to prove any particular number is transcendental. However, somehow the transcendentals are much more numerous than the algebraic numbers, even though they are both infinite sets. You can make that precise when you learn real analysis.